Alright, in this chapter we're going to talk about paired samples and blocks. Still two sets of data where we're going to be interested in mean values, but a little bit different than chapter 23. So let's go explore the differences. We're going to look at data collected from subjects that have been paired up, and this could be two different people or objects or whatever, two different measures that have been paired up, or in the case of people it can be like a situation where it's a measurement before and after some experiment. We want to test whether the means of two groups are equal, but we can't use the independent two-sample t-test like we did in the last chapter. What we're going to do now, the procedures we're going to use here are basically the procedures that are similar to the one-sample t-test. We're going to apply these methods to the differences observed between two measurements on each pair. So we're going to take the difference of two measurements for each pair of numbers, create kind of like a third column of data with all the differences, line by line differences. That third column with only the differences is what we're going to use to do our inference testing. So sometimes it helps to think about one set of data in list 1, the paired set of data in list 2, create a new list 3 with the differences row by row, and then we're going to do our inference on the difference numbers in group in list 3. So the problem that we're going to have here is less about what techniques we use, and it's more about learning how to perform this kind of inference, or how to decide which inference method to use. So it's less about how to perform the mechanics and more about when to choose a two-sample t-test or a one-sample t-test. So the data are two different measurements for the same group of people, or two different groups in which individuals were paired. In chapter 23, one of the requirements and the conditions was that the groups be independent of one another. Pretty obvious now that we have pairings based on some meaningful purpose, so they're not independent. Sometimes also we have before and after data for the same people, and that obviously those data values are also not independent of one another. So the decision about what procedure to use must be, you got to use the way the data was collected and think about the problem itself. You got to think before you do the show and tell. They're not going to always tell you what you need to do. In fact, some of the worksheet problems that I've given you for homework is for you to have to decide which situation it is. Even bigger than that, all the way back to chapter 18 and then all the way through chapter 26, even though we may not get there, is all full of different methods that we normally would have to deal with. So it's fine when those problems are kind of chapter by chapter, but when they're all grouped up and mixed together, and any of them can show up, say on a final exam or on the AP exam, then, it's a little bit more of a challenge and it's more important to, at the beginning say, well, based on the design of the problem, this is the kind of inference procedure that I need to use. And it turns out, you guys, that even, the students that are really good in the mechanics and all sometimes may have a little bit of trouble deciding, which type of problem that it is. So basically just practicing is what it's going to take. Notation is important. Proper notation is going to help you with understanding and communication of your work and your solutions. So new for this chapter then, since we're going to be talking about the distribution of the differences in paired data values, we need to make markings or notations that indicate that. So we're not really comparing the overall means of the two sets of values. We're looking at the average of all the differences. Okay, so our sample statistic is going to be the mean of the differences, and we're going to use the letter D for this, not the difference of the means. Say y1 minus y2. This is a very important distinction between these two things. So the mean of the differences is what we're doing now. And what we did before was the difference of two sets of means. Each stage of the procedure reflects the fact that we are looking at paired differences rather than independent measures. So, without the independence, there are some rules that change along the way. First of all, the hypothesis is about the mean of the differences. So take a look at this notation. We get the mean symbol, and then sub D meaning it's the difference. So we would have already, row by row, calculated, say like y sub 1 minus y sub 2 for row 1, and doing the same thing for row 2, row 3, row 4. We're taking all those individual differences and averaging them. The data are paired, so we're going to look at the histogram not of the two individual data sets, but of the differences of the data sets. So like this third list that I was talking about, create a new list of just the differences from list 1 and list 2, and then that is the data you'll use to make your histogram. So we only have one histogram, not two. So as you can see, since we're only going to be working from a single list, the method will look more like the one sample T approach. The difference is we're talking about the mean of the differences, not just the mean of the data. Two lists are involved, but it's still not a two sample T test. Okay. We will use degrees of freedom here, and the degrees of freedom kind of get simplified again. It was a little more complicated in the last chapter. Degrees of freedom is number of pairs minus 1. And in this case, we're starting with two different lists. Those two lists have to be exactly the same length because it is paired data now. Alright, we're going to talk about, our inference will tell us what the data reveal about the average differences, average of all the differences. So example statements might be like, there's strong evidence that a training program results in an increased test score on average. So the increased test score is what we're seeing line by line, and we're talking about the average impact of that. Here's another one, a confidence interval. We're 95% confident that the training increases an individual's test score by an average of between 8 and 10 points. This one's pretty clear to see that we're talking about a single person's test score changing or increasing, and then we're looking at an average increase of test scores for a whole set of individuals. Pairing is a form of blocking in certain experiments, and so when you can see that, when that's evidenced by the description of the problem, it's kind of easy to see that that it is, the mean of the differences. Observational data, that could be matched up in a lot of different ways, or blocked. Say for an experiment, the blocking just could be a method of randomizing. Makes the pairing a little less clear. A perfect example of this is, what if we had 50 men and 50 women in a study? Maybe they could be paired just because of the difference in gender, and the experimenter wanted to reduce that as a bias. But, if the pairings are because they're 50 married couples and it's husband and wife being paired up, then that's a different situation. There's a difference there with independence, for sure. I'm going to complete this video here and call it the introduction video and do the class example in a separate video.